Imagine, if you will, a universe where the most distant galaxies are within our reach, not by the electrochemical bonds that power today's rockets, but by harnessing the boundless energy of the stars themselves. As we gaze upward, dreaming of venturing beyond our own blue planet, we find that our ambitions are often curtailed by the very technology designed to propel them. For decades, humanity has danced on the lunar surface and skimmed the edge of distant worlds, yet it's our energy sources, finite and fossil, that have kept us tethered close to home. Here lies the frontier of fusion energy, a realm of science fiction fast converging with reality. Unlike the fission reactions that have powered our nuclear ambitions for years, fusion is both a cleaner and virtually limitless source of power, mirroring the very processes that fuel the sun. The dawn of fusion energy is heralding a new era of space exploration, promising propulsion systems that vastly outperform today's outdated combustion engines. In this video, we delve into the promise of fusion, examining its theoretical potential, its feasibility, and how it could transform the mechanics of space travel as we know it. From significantly reduced travel times to the prospect of long-term energy independence in space, the impact of fusion technology is immense. So, join us on this journey as we explore how fusion energy is set to revolutionize our journey into the cosmos, reshaping the future of spaceflight. Now turning to understanding fusion energy, picture the sun as a massive celestial furnace. Its core operates through a process of fusion, where hydrogen atoms merge to form helium, releasing an enormous amount of energy. This reaction is the essence of fusion energy, a concept not unlike the sun's power but harnessed here on Earth. The fusion process is fundamentally different from fission, the reaction used in traditional nuclear power plants. While fission involves splitting heavy atomic nuclei to release energy, fusion merges lighter nuclei, generating energy without the harmful radioactive byproducts that accompany fission. This makes fusion a much cleaner energy source. Fusion holds the allure of being virtually limitless as the primary fuel, isotopes of hydrogen, are abundant in water. At present, the scientific community views fusion as the holy grail of energy solutions. However, despite its promise, achieving controlled fusion on Earth has proven immensely challenging. The conditions needed to sustain fusion reactions are extreme, requiring temperatures that rival the sun's core. Containing such reactions demands advanced technology and materials that can withstand these intense environments. Today, major players in the race for viable fusion power include international collaborations like the ITA Project in France, which aims to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. According to Dr. Maria Zuber, a leading figure in fusion research, fusion energy is like trying to hold a star in a bottle, a monumental challenge, but one that could supply the planet with abundant energy. Projects like ITER are indeed ambitious, but they represent only a part of the global effort. Numerous startups and governments are investing in alternative approaches, such as magnetic confinement and inertial confinement, to achieve sustainable fusion reactions. The promise of fusion energy extends far beyond just power generation on Earth. As we seek new frontiers in space, fusion could revolutionize propulsion systems, enabling spacecraft to journey greater distances with unprecedented efficiency. In this light, fusion energy stands as both a daunting challenge and a beacon of hope, holding the potential to transform our future both on Earth and beyond. As the next phase of this journey unfolds, we continue to explore its profound implications for space travel and energy independence in the cosmos. With the next phase of the journey in sight, imagine the early days of fusion research as a tale of curiosity and ambition, with visionaries eager to replicate the sun's energy here on Earth. In the mid-20th century, scientists were captivated by the idea of fusion, a phenomenon that promised inexhaustible energy. Their early experiments were rudimentary but paved the way for a series of breakthroughs. By the 1950s, the global scientific community began earnest endeavors to achieve controlled fusion. This decade marked the birth of some of the first experimental reactors, designed with the aspiration of sustaining the high temperatures needed for fusion. It was a time of spirited international competition and collaboration, as various approaches to fusion containment were explored. Among these, magnetic confinement emerged as a leading strategy, where powerful magnetic fields attempt to hold the hot plasma, akin to a donut of fiery gas within a reactor. This method led to the development of the tokamak device, a cornerstone in fusion research. By the late 20th century, another approach, known as inertial confinement, gained traction. Here, high-energy lasers compress small fuel pellets, creating the extreme conditions necessary for fusion. Both methods seek to create environments mimicking the intense heat and pressure found in stars. As we moved into the 21st century, these technologies matured significantly. A landmark moment in fusion's timeline is undoubtedly the ITA Project. As an international collaboration involving 35 countries, ITER represents humanity's collective pursuit of fusion energy. Located in France, this facility is designed to demonstrate the feasibility of fusion as a large-scale, carbon-free energy source, setting a precedent for future reactors. Alongside ITER, numerous countries have embarked on their own projects, fostering an unprecedented surge of innovation and sharing of knowledge. Today, as we stand on the threshold of turning these technological advancements into practical applications, the implications for spacecraft propulsion are particularly exciting. With fusion's potential to provide immense energy, spacecraft could traverse the cosmos with unparalleled efficiency and speed, no longer tethered by the limitations of chemical propulsion. This transition could usher in a new era of space exploration, fundamentally altering how humanity views its place in the universe. Hence, the journey of fusion technology, from its humble beginnings to its current cutting-edge research, underscores a persistent quest for energy solutions that might one day power our endeavors beyond Earth. As the next challenge unfolds, consider the story of Robert Goddard, the pioneer of modern rocketry, who faced immense skepticism and technical hurdles. His relentless perseverance is a testament to the spirit required to conquer the challenges of harnessing fusion energy. Fusion research, like Goddard's journey, is fraught with formidable obstacles, yet driven by the promise of revolutionary breakthroughs. One major hurdle lies in achieving sustained reactions. Fusion requires temperatures hotter than the sun's core, which is a feat that demands not only immense power, but also innovative solutions to contain and sustain these reactions within a reactor. Material durability presents another significant challenge. The high-energy neutrons produced in a fusion reaction can damage and degrade reactor materials over time, necessitating the development of materials that can endure these extreme conditions. This is where the quest for robust, heat-resistant materials becomes crucial, as scientists strive to engineer components that withstand continuous exposure to such intense environments. Energy output efficiency is also a critical consideration. The goal is to generate more energy from a fusion reaction than is consumed to initiate and maintain it, a delicate balance that has yet to be achieved at a practical, scalable level. This aspect of fusion research demands cutting-edge technology and innovative engineering to enhance the efficiency of energy conversion and extraction processes. Addressing these challenges requires pioneering engineering solutions. Advanced materials that can endure the punishing conditions inside a fusion reactor are being developed with an eye toward longevity and cost-effectiveness. Containment solutions, such as those employed in tokamak devices, are being refined to improve magnetic field strength and stability, crucial for maintaining the delicate balance needed to sustain a fusion reaction. Expert insights reveal the complexity of these tasks. Scientists and engineers worldwide are collaborating, sharing knowledge and innovation to advance fusion technology. The iterative nature of this research underscores the importance of perseverance and collaboration in overcoming the technical challenges that have historically stalled progress. Now, envision how these advancements in fusion can benefit space exploration. The ability to generate immense energy could revolutionize spacecraft propulsion, allowing vessels to travel farther and faster than ever before. With fusion-powered propulsion, the constraints of chemical fuel are lifted, opening possibilities for more ambitious missions to distant planets. This newfound capability could lead to a new era of exploration, with fusion-powered spacecraft capable of sustained journeys and enabling humanity to venture deeper into the cosmos. As such, the pursuit of overcoming fusion challenges not only holds promise for energy here on Earth, but also for expanding our reach among the stars. Moving forward, picture a spacecraft gliding through the vast emptiness of space, powered not by the burning of chemical propellant, but by the immense energy of fusion. This isn't the stuff of far-off science fiction. With fusion propulsion, spacecraft could achieve velocities that were once unthinkable, slashing travel times between planets. Traditional chemical rockets dependent on limited fuel impose severe restrictions not only on the speed and duration of space missions, but also on the weight they can carry. In stark contrast, fusion engines promise a new paradigm in propulsion. By using a tiny amount of fuel that can generate enormous energy, they can propel spacecraft more efficiently and for much greater distances. Imagine launching a mission to Mars not with months of travel ahead, but with weeks. This would revolutionize our approach to space exploration, opening up avenues for more frequent and extensive scientific endeavors. The sustained power supply provided by fusion would ensure that missions are not only faster but also more reliable. Long-duration missions, perhaps even extending to our more distant planetary neighbors, could become practical as the energy demands are continuously met without the need to return to Earth for refueling or resupply. Fusion propulsion also has the potential to redefine spacecraft safety and design. The mass of spacecraft has always been a critical factor, with every additional kilogram requiring significant propulsion power. With fusion, the mass can be significantly reduced. The efficient energy output of fusion engines means that spacecraft can be designed with lighter and more durable materials, enhancing safety without sacrificing performance or capacity. This reduction in mass also lowers the risk associated with launching heavy rockets, minimizing the chance of launch failures. Looking at current conceptual designs and emerging prototypes, there are promising indications of what fusion-powered spacecraft might look like. Engineers and scientists are exploring various configurations, such as fusion drives that use magnetic fields to contain and direct plasma. Projects like the Direct Fusion Drive are investigating how to harness this technology for interplanetary travel, aiming to create engines that are both powerful and manageable. These designs are not just theoretical but are slowly pivoting towards practical application, showcasing a future where fusion energy is the norm in space travel. The road ahead is challenging, yet the potential rewards for humanity are immense. Fusion energy holds the key to unlocking the mysteries of the universe, offering us the chance to explore the cosmos more deeply and meaningfully than ever before. As we continue to advance in our understanding and application of fusion technology, it's exciting to consider how it might reshape our destiny among the stars. Now turning to a comparison with current space propulsion technologies, let's first revisit the engines that have long propelled us beyond Earth's atmosphere: chemical rockets. These have been the mainstay of space travel since the mid-20th century, relying on the combustion of propellant to generate thrust. While groundbreaking in their time, chemical rockets have their share of limitations. Imagine a horse-drawn carriage. It can certainly get you where you need to go, but not with the speed or efficiency of a modern car. Similarly, chemical rockets are bound by the constraints of their fuel-heavy, finite, and only capable of carrying missions so far or fast before exhausting resources. They require large amounts of fuel, imposing strict limits on payload size and mission duration. These constraints inherently limit the scope of space exploration, making extended trips and the transport of substantial cargo challenging. In contrast, fusion energy presents potential that could redefine these boundaries, like shifting from that horse-drawn carriage to a sleek, modern vehicle. Fusion propulsion promises not just higher efficiency, but the ability to sustain missions over significantly longer periods. With the immense energy output of fusion, spacecraft may carry less fuel, thereby accommodating more scientific instruments or cargo. This transition is akin to replacing the sputtering gas engine with a powerful, ultra-efficient electric motor, transforming everything from performance to capacity. Fusion's applications could revolutionize specific space endeavors. Consider deep space missions currently restricted by the necessity to return or refuel due to finite resources. Fusion could enable spacecraft to venture further and longer, maintaining a steady and robust power supply throughout the journey. Or think of lunar bases. With fusion, these could be supplied continuously with power, eliminating dependency on periodic supply missions from Earth. This could open up a whole new realm of sustainable exploration and colonization possibilities. The transformative possibilities of fusion in space travel are vast. What if we could travel to the outer planets not in years but in months? How might fusion technology alter the very fabric of our approach to exploring the cosmos? Fusion propulsion offers not only efficiency and endurance, but also the potential to reshape our aspirations and methods in the exploration of space. The implications are profound, suggesting a new era where our reach into the universe is limited only by our ambition and ingenuity. Now turning to case studies on current fusion research projects, let's explore how these initiatives are pushing the boundaries of space technology, bringing us closer to a future where fusion powers our spacecraft. At the forefront is the Princeton Field Reversed Configuration, or PFRC, which is pioneering new methods to harness the power of fusion for space applications. The PFRC focuses on a compact fusion reactor design, which seeks to achieve high energy efficiency and manageable size, ideal characteristics for spacecraft integration. This approach utilizes magnetic fields to confine plasma, aiming to sustain stable reactions necessary for effective propulsion. As researchers at Princeton work tirelessly, the project shows promise in creating engines that might one day propel spacecraft far beyond our current reach. Meanwhile, Helion Energy is making significant strides with its innovative work on fusion rockets. Helion's unique approach involves direct energy conversion, which could potentially revolutionize how power is utilized and transferred in space. This technique not only enhances energy efficiency but also reduces the complexity of power systems on a spacecraft. Helion aims to create a compact, portable fusion reactor that can be used effectively in challenging environments like outer space. Their approach stands out for its focus on scalability and adaptability, critical factors when considering missions beyond Earth. In addition to these major players, numerous other projects contribute to the rapid advancements in fusion technology. Each project, while distinct in its methodology, shares a common goal: to realize fusion's potential as a viable spacecraft power source. This collaborative effort is slowly but surely breaking down the barriers that have kept fusion from being the foundation of our space exploration endeavors. Researchers and engineers are constantly refining techniques, addressing challenges such as sustained reaction stability and material resilience against extreme conditions. By doing so, they are laying the groundwork for what could be a breakthrough in how we think about powering space travel. These projects exemplify the innovative spirit required to bring fusion technology from theory to practical application. By showcasing the progress and determination of these teams, we gain a clearer picture of the future where fusion-powered missions become a reality. As the next phase of the journey in fusion research unfolds, the potential for space exploration expands exponentially, paving the way for limitless possibilities in our quest to explore the cosmos. With the next phase of the journey in sight, envision a spacecraft powered by fusion energy embarking on a groundbreaking mission to Mars. Imagine a sleek vessel, fueled by the same energy that powers the stars, gliding through the vast expanse of space with unprecedented speed and efficiency. The promise of fusion technology lies in its ability to drastically reduce travel times, potentially cutting the Mars-bound journey from several months to just a few weeks. This speed not only enhances the feasibility of long-duration missions, but also opens new doors for scientific exploration and human settlement. Picture astronauts aboard this fusion-powered craft, empowered by a virtually unlimited supply of energy. This abundance of power enables them to conduct extensive research and experiments, pushing the boundaries of our scientific understanding. Fusion reactors can provide a continuous and sustainable power source, crucial for operating life support systems, communication networks, and scientific equipment needed for a successful mission. Such capabilities give astronauts the ability to explore Mars and beyond with a level of autonomy that current technology cannot support. Beyond just getting there faster, fusion propulsion offers transformative flexibility. Missions are not constrained by the limitations of traditional chemical propulsion, allowing for rapid directional adjustments and extended stays on extraterrestrial bodies. This flexibility means that missions can adapt on the fly to unexpected discoveries or changes in mission objectives, maximizing the scientific return of each trip. New pathways for interplanetary travel become viable, potentially altering trajectories to explore new regions of the solar system. These advancements align seamlessly with current scientific aims, such as searching for signs of life on Mars or studying the planet's geology and climate in greater detail than ever before. As we pursue these objectives, fusion technology holds the key to unlocking new realms of the cosmos. It brings us closer to achieving long-held dreams of establishing human outposts on other planets, contributing to our understanding of the universe and humanity's place within it. Imagine the ripple effects entirely new industries could emerge as fusion-enabled spacecraft become a cornerstone of space exploration. This shift would catalyze advancements in technology, science, and even philosophies about our existence in the universe. As we stand on the brink of this technological revolution, we invite you to ponder how fusion might redefine our approach to the cosmos, potentially transforming our understanding of life beyond Earth and inspiring a new generation of explorers poised to journey further than ever before. As the sun rises on the next chapter of our journey into the universe, we consider the legendary vision of Carl Sagan, who once said, "Our planet is a lonely speck in the great enveloping cosmic dark." This perspective urges us to be stewards of Earth, using technology that respects and preserves our fragile home. Fusion energy represents a beacon of hope in achieving sustainability, especially in terms of space exploration. Fusion-powered spacecraft offer significant environmental advantages compared to traditional propulsion methods. Unlike chemical rockets that rely on burning massive amounts of fuel, fusion propulsion systems generate negligible emissions. This reduced environmental footprint is crucial as we strive to minimize our impact on Earth's atmosphere and beyond. Moreover, the resources required for fusion reactions, primarily isotopes of hydrogen, are abundant, ensuring a sustainable supply without the ecological footprint associated with mining and refining rare materials. Beyond environmental considerations, fusion technology promises transformative economic potential. Its unparalleled efficiency and minimal fuel requirements could drastically cut the cost of space travel. This affordability opens the heavens to a broader range of missions and entities, from scientific expeditions to commercial ventures. As fusion-powered spacecraft become more common, we could witness a surge in the space industry's growth, stimulating innovation and creating new opportunities not just for established companies but for emerging players as well. The ripple effects of these advancements extend to global economic landscapes. Fusion technology could unlock previously unimaginable space industry markets, potentially becoming the backbone of a new era of space-related services. This growth could stimulate job creation across numerous sectors, from engineering and research to logistics and infrastructure development, fostering a robust economy centered around space exploration and technology. Fusion-powered initiatives also promise to revolutionize sustainable space exploration. The ability to generate power continuously means missions can be prolonged indefinitely, offering unprecedented flexibility in planning and executing scientific research. This capability supports the establishment of permanent human outposts on other celestial bodies, enabling a balance between exploration and preservation. As we consider the future, these environmental and economic implications could profoundly influence global space policy and innovation. Nations may come together, fueled by the promise of clean energy, to collaborate on fusion projects that not only enhance our understanding of the universe but also foster peace and cooperation on Earth. Fusion energy, once a dream confined to science fiction, edges closer to reality, offering a path toward a more sustainable and economically viable future in space exploration. As we stand on the threshold of this new frontier, we invite you to reflect on the transformative power of fusion and its potential to reshape our relationship with the cosmos. With the next phase of the journey in sight, we envision an exciting future where fusion energy spearheads human exploration of the cosmos. Imagine spacecraft powered by this transformative energy source, navigating the vastness of space with efficiency and grace. As we advance, several key milestones in fusion technology could reshape the landscape of space travel. One such milestone is achieving sustained and controlled nuclear fusion reactions, which are crucial for reliable and safe propulsion systems. Researchers are making significant strides in developing compact fusion devices tailored for space applications. These innovations promise a future where fusion-powered spacecraft become the standard, reducing travel times and expanding our reach into the universe. A dynamic partnership between public and private sectors also emerges as a catalyst for progress. Governments and space agencies, along with visionary private companies, are pooling resources and expertise to accelerate fusion research. Initiatives such as international collaborative projects could pave the way for shared knowledge and technological breakthroughs that benefit all of humanity. This cooperation opens doors to unprecedented levels of innovation and resource sharing, potentially accelerating the timeline for practical space applications of fusion energy. Speculating further, we can foresee remarkable possibilities like colonizing moons or asteroids with fusion-powered infrastructures. These futuristic habitats could thrive using the virtually limitless energy provided by fusion, enabling sustainable life support systems, advanced research facilities, and thriving communities beyond Earth. This vision aligns with our innate curiosity and ambition to explore, offering a glimpse into a future where space is an extension of our world, not just a distant frontier. As we ponder these advancements, the societal implications are profound. Fusion energy's potential to revolutionize space exploration could redefine how we perceive our place in the universe. It inspires a shift towards international collaboration, where nations unite to harness clean, limitless energy for the common good. This pursuit of a shared future in space could foster peace and understanding on Earth as we work together to overcome challenges and unlock the mysteries of the cosmos. As the sun continues to rise on this incredible journey, we invite you to contemplate the far-reaching possibilities that fusion energy presents. How might our relationship with the cosmos change in a world where fusion powers our every step among the stars? The journey is just beginning, and the potential for transformation is immense, inviting us all to dream bigger and aim higher in our quest to explore the universe. Now turning to potential challenges and critics, it's essential to recognize that even the most revolutionary technologies encounter their share of skepticism and hurdles. When it comes to fusion energy, significant obstacles remain that could slow its integration into space technology. One major challenge lies in scaling the technology from Earth-based reactors to space-ready systems. Developing compact and efficient fusion reactors capable of operating in the challenging environment of space is a formidable task. This requires not only engineering breakthroughs but also advancements in materials science to ensure systems can withstand the harsh conditions of space travel. Another critical concern revolves around cost. The investment required to advance fusion technology to a point where it is feasible for space travel is immense. Critics highlight the financial risks associated with such investments, questioning whether the returns justify the expenditure. This is compounded by the uncertainty of timelines, as achieving practical fusion energy for space use could take years, if not decades, to become a reality. Feasibility also comes into question, with some skeptics arguing that the complexity of fusion technology may make it an impractical solution for near-term space exploration. The intricacies involved in sustaining and controlling fusion reactions, particularly in the unique conditions of space, add layers of difficulty that some believe may be insurmountable with current technological capabilities. However, it's important to counterbalance these critiques with the ongoing research and development efforts in the field. Expert opinions suggest that while the path to fusion-powered spacecraft is fraught with challenges, the potential rewards make it a worthy pursuit. Researchers are actively working on innovative solutions to overcome these hurdles, developing more efficient reaction mechanisms and exploring novel engineering designs that could make compact fusion reactors viable for space missions. Additionally, public-private partnerships and international collaborations are pivotal in addressing these challenges. By pooling resources and expertise, stakeholders can share the financial burden and accelerate progress, potentially bringing fusion technology closer to fruition. These cooperative efforts are essential in transforming what was once considered a distant dream into a tangible reality. In summary, while the road to utilizing fusion energy in space is littered with obstacles, the commitment to overcoming them is strong. The criticisms and challenges are valid, but they also serve as a catalyst for innovation and resilience within the scientific community. As we advance, these hurdles will likely lead to exciting breakthroughs that will not only benefit space exploration, but also have far-reaching implications here on Earth. As we draw our discussion to a close, let's take a moment to reflect on the extraordinary journey of harnessing fusion energy for spacecraft technology. From its potential to revolutionize space travel with unprecedented efficiency to the challenges faced along the way, fusion energy stands as a beacon of innovation. It's a tale of scientific perseverance, where the dream of sustainable space exploration edges closer to reality with each breakthrough. The promise of fusion energy is not just limited to powering our spacecrafts. It represents a new era of exploration and sustainability. It embodies the very spirit of human ambition, the relentless quest to push boundaries and explore the unknown. Imagine a future where journeys to distant planets are not limited by fuel constraints, where the vastness of space becomes more accessible. This vision of fusion-powered exploration not only inspires us but also propels us towards developing a sustainable future. As we contemplate the possibilities, consider the profound impact this technology could have on our understanding of the cosmos and our place within it. It's a reminder of what humanity can achieve when we dare to innovate. Let's ponder this. What role might fusion energy play in our future missions beyond Earth? Could it be the key to unlocking new frontiers and discovering new worlds? As you reflect on these questions, we invite you to share your thoughts and experiences in the comments below. Engage in the conversation about our incredible future powered by fusion energy. Your insights are invaluable, and your participation shapes the exploration narrative. Lastly, if you're as excited about the potential of futuristic technologies as we are, don't forget to subscribe to our channel. By joining our community, you'll stay informed with the latest insights and discoveries in the realm of advanced technologies that will redefine our future. Thank you for being part of this journey, and we look forward to exploring the next chapter of space exploration with you.